Welcome back to this course on polymer chemistry, and in today's lecture we are going to start our discussion on polymer properties and how they are evaluated, those properties are evaluated. And today we will start our discussion on mechanical properties, which may be continued in the next lecture as well, and then eventually we will discuss very briefly the other properties. Now, this lecture and probably next one or two lectures is not directly related to chemistry per se, but as a polymer chemist, if you are hired in a company, then you must know the polymer properties, because this is when you doing some polymer synthesis and characterizing them, finally you are targeting for some application, and applications are linked with polymer properties. So, unless you do not know what the polymer properties means, how they are evaluated and how they are related to the polymer structures, then it is difficult for you to design a new polymer and then synthesize it. So, it's very basic need to understand the polymer properties, at least in brief. And out of the polymer properties, I will spend more time on basically we will discuss in little detail about mechanical properties, because as you will see in next one or two lectures, this is the most important properties of the polymers, and some other properties like thermal properties, environmental properties, they are linked to the mechanical properties. Linked means what I mean that basically the polymers are exposed or bring in contact with heat or some environment conditions, and then the properties, mechanical properties of polymers are followed according after exposure. So, mechanical properties is the most property for polymer, and I will discuss the mechanical properties in detail, and I will very briefly cover the other properties like thermal, environmental, barriers, surface, electrical, optical, fire resistance, etc. And before I start discussion on polymer properties, I want to very briefly talk about polymer processing, mainly because the fact that till now we have understand or we have gained the knowledge of polymer resins, how to synthesize them, how to characterize them, and then finally these polymers will be applied in product, in applications, and the step which converts the polymer resins into product is called processing. So, polymer properties are tested on the final product or final specimens. So, unless we know the polymer processing step, there will be gap between a resin and a product or application. So, this is again not directly related to chemistry, but you must know the basic nomenclatures and basic techniques how by which the polymer is converted from a resin to a product for final applications. So, let us start our discussion on polymer processing very briefly. As I said, polymer processing can be done from a melt state or a solution state. Melt state, there are 2-3 techniques, mainly extrusion, molding, thermoforming, by which the polymer are converted to final specimen. And for solutions, we can do casting is applied to making films, and spinning is applied to both from polymer melts or polymer solutions, for example, making fibers. Now, as I said that the polymer processing from melt state are mainly 3 types. We can mainly 2 types, we can say extrusion and molding. Extrusion is basically a step where compounding means mixing is done between the polymer resin and other additives or reinforcement, colorant and all these things, and then taken to the molding state to give the final part. Or extrusion techniques can be used for making final parts, like very simple parts like film profiles like pipes, rods and so on. Moldings are these are techniques of molding: injection molding, blow molding. These are applied for thermoplastics, and compression molding, transfer molding, these are applied for thermosets. So, what I will do, I will discuss these techniques, important techniques like compounding, injection molding, blow molding, compression molding in very briefly, so that you know, you have some idea about how this extrusion molding is done. So, how as an overview of melt processing technique, there is a formulation where this solid polymer is added, and if you need additives, and invariably we need rarely that the 100% polymer is used for any formulation. There will be invariably some additives added, and they can be mixed well, and if there are color master batch or some other master batch, they can be added here. So, this is the formulation, and then they are taken to melt processing steps like extrusion. It could be 2-step extrusion followed by molding, or it can be just extrusion step, and then you finally get the specimen where some post processing steps are done. Like for example, if you are making a DVD, then the polymers are taken and then extruded and finally injection molded to a DVD form, and then the company takes it and put the data in it, and put the decoration and finally sell it as a product. In this state, you can add other agents like foaming agents, which makes the final product foam product, or you can add the other fillers and reinforcement material. Typically, amorphous materials are processed, melt process at Tg plus somewhere 80 to 140 degree centigrade temperature higher, and semi-crystalline materials are processed at melting temperature plus a temperature of 20 to 50 degree centigrade. Talk about briefly extrusion process. Its extrusion process, as said, is a steady state process. It is a continuous process having high productivity, and it is used for making low complexity of parts like pipes, sheets and so on. This is a schematic or structure or scheme of a extruder, where extrusion is made. One screw is shown. This is a single screw extruder. There in some other cases there could be 2 screw, which makes that instrument as twin screw extruder. It has different zones having different temperature, with increasingly, if you go from left hand side to right hand side, the temperature generally increases and becomes steady somewhere in this region, and there is a die by which the molten polymers are extruded out and cooled, whether air cooled or cooled in water medium. It could be cooled in both the ways. So, basically in the first part, all the ingredients are added, and those ingredients are mixed here, molten in this part, melted in this part and mixed thoroughly, and as the screw rotates, the melt is pushed forward, and finally the melting and mixing is completed here, and this polymer melt comes out from this die. And if you have different shaped die like sheets, you can form sheets or pipes here itself, or if you want to use this material for further injection molding or some other molding step. You can cut into granules in small pieces and make them as a granules. Some other large companies, large polymer manufacturing companies, they just mix all these ingredients and extrude the polymer and make granules and sell those granules in big bags, and those are purchased by the final or original equipment manufacturer. They just take those granules and do the molding, and they are in to make the final product. So, the function of extruder is to pump the high viscosity melt, also mixing the ingredient. Sometimes if you add some, if you deliberately want some reaction to happen at higher temperature, then you can do in extruder. Sometimes there unwittingly or unwantedly some reaction also take place inside extruder, and if there are volatile materials, then you can add some vacuum somewhere here to remove those volatile materials. So, going to molding, and molding is a cyclic transient process, and use of molding can be used for making complicated 3-dimensional parts. As I said, it could be injection molding, blow molding, thermoforming. Injection molding is done mainly for thermoplastic material, and it is similar to the extruder machine. There is a hopper where you add the granular polymer material and some additives which act as a mold release agent, so that after the part is formed, it can be easily taken out from the mold. There are screws. It basically melts and mix those polymer with the additives here, and this screw, by rotating it, takes it forward. There is a cylinder somewhere here which basically pushes the polymer melt, mixed polymer melt in the mold, and one molding is done, it is cooled and the part is ejected from this material, this mold. Other techniques like extrusion blow molding, where the extruded polymer is placed in form a tubular profile. It is like this is a tubular profile, and it is placed inside the mold, and then the inert gas is injected through to inflate this tubular profile till it gets the shape of the mold, and finally it is cooled here and the part is taken out. It is used mainly for bottles, hollow materials like bottles and similar materials. Similarly, in addition to extrusion blow molding, injection blow molding also can be used, where this paration, this tubular profile is basically injected in this mold, and the rest of the steps are similar, where the mold is inflated with the inert gas and then cooled and the part is taken out. So, injection blow molding and extrusion blow molding are similar, except the way this paration is inserted in the mold. So, this scheme is shown here. The other techniques, in very briefly, thermoforming, where a sheet is first extruded and then it is heated to a temperature just below the it is heated to a softening temperature, and then vacuum is applied, so that this sheet is formed, can be thermoformed in the shape of the mold. Similarly, in injection molding machine, this is the place where the polymer melt is accumulated. Now, in this case, if you want to make a foamed polymer, you can add some inert gases here and then make a short, which means you can inject less material which was supposed to be filling the entire mold. So, then what happens, this material fill the mold with this gas in a foamy form in between. So, the surface would be in contact with the mold, it will be plain, which will not have any bubbles. So, it will be smooth, but the bulk will have lots of inert gases as a foam. So, you can get a foamy material. So, thermoset polymers are molded using compression molding. Basically, as you know that thermoset polymers cannot be flown at higher temperature. They are cross-linked material, so they do not flow. So, basically what you do, you basically melt in a cavity, and then with a particular shape mold you just compress them and leave it. You close this, compress them and close it, and once it cools you can take out this mold and you can form this shaped article or part. So, this is in brief about compression molding. So, now we have seen how these polymers are converted to the articles. Now, we will discuss about the properties of this final polymer, and these properties are very essential for the applications. So, you have to make a polymer article or part having particular properties, so that it can sustain or you can apply it to the application you are looking for. And as I said that I will be mainly will be discussing the mechanical properties in details. Some basic terms in when you talk about mechanical properties. Stress, you know that it is force divided by the area upon which the force acts. So, it is a stress is given by force. So, stress is force by area, and strain is basically is the change in dimension divided by the original dimension. So, if you talk about length, then it will be change in length by total length. Typically, we express strain in terms of percentage. So, strain percentage is given by dl by L into 100. So, that is the strain percentage. We will be using the stress and strain very frequently in coming discussion. Now, mechanical properties is polymers mechanical property is related to the deformation. What happened in when you apply some force or a stress to polymeric material, a plastic material, it deforms, and the deformation behavior is basically what we discuss or the talk about mechanical properties. So, you first know how many different types of deformation a polymer may undergo under applied stress or applied force. So, there could be three types mainly. One is elastic deformation. You probably know that we say that elastic deformation happen when a material returns to the original state, releasing the stresses following the same stress strain curve that it took during deformation. So, while if you apply stress, it will deform. If you release the stress, it should come back in the same path, stress strain come to the original state. Then we call this as a linear, this as elastic deformation. It could be linear if the stress strain behavior is linear. So, it goes from here and come back in the same path. It is a linear behavior, and if it is something like that, it goes in this way and come back, then it is a non-linear elastic behavior. Second is your inelastic deformation, where basically inelastic behavior, what happens if you give the stress, give the force, the energy is stored in the material. So, when you release the stress, that energy is given back. So, you get back to the original state. Whereas, in case of inelastic deformation, when you apply the energy or apply some force, the energy is lost. So, it may deform permanently, or it even if come back to the original state, it do not follow the same path. So, in elastic deformation, loss of energy happens, and if at all it returns to the original state, then it does in a different route. It could be two different types: viscoelastic, which may and may not show permanent deformation, and there is another type of deformation where plastic deformation, where permanent deformation happen. So, plastic deformation is said to have occurred when the deformed material is permanently unable to return to its initial state, and yield point is that where the material start showing the plastic deformation. What happened at molecular level in elastic during elastic registration, the resistance to deformation can happen both intermolecular. The polymer chains are entangled to each other. So, polymers, the resistance to deform may happen because of presence of the other polymer chain segment in the near vicinity, or it could be due to resistance due to intramolecular, because polymer chains are entangled. So, different parts of the chain are linked. So, they resist they resist to give resistance to deformation. Elasticity in elastomer, elastomers are very elastic. So, it elongates quite high, and entropy change on deformation is the dominant factor to the resistance of deformation. In case of elastomer, the polymers are having a conformation, coil type conformation in normal case. So, if you write just polymer chain conformation like this, and in real polymer they are basically different chains are entangled with each other. So, if you want to stretch, deform it, like in elastomer what happened, these conformational entropies are lost. So, when you release that stress to gain that conformational entropy, it comes back to its original state. So, that is what this entropy change on deformation is the dominant contribution in to the resistance of the deformation in case of elastic material. And in case of plastic deformation in the polymers, especially in case of amorphous polymers, cooperative motion of a large number of chain segments happen together. Large number of chain segments cooperatively move with each other, and in case of semi crystalline polymer, deformation at crystallographic scale, crystal state. So, polymer chains might slip with respect in the direction of the applied stress, or it could move in the perpendicular direction, and there could be deformation in case of semi crystalline polymer, could be deformation in the amorphous region, or in case of the spherulite region. So, mainly we talking about elastic deformation and plastic deformation. Elastic deformation, where on applying releasing the stress, the sample comes back to the original state, and in case of plastic deformation, it does not come back. The polymer sample on releasing the applied stress does not come back to the original state. There is a permanent deformation. So, when you test the mechanical properties there are different types of tests can be conducted. Static states test like tensile, compressive shear properties, which gives stress strain curves, stiffness and strength and toughness of polymeric material. We impact test, which is basically high strain rate test, done it very fast, by applying stress in a fast rate, and it can give the impact strength, the resistance of a plastic material to impact can be given by impact trace, and time dependence behavior of polymer material can be done from a creep test. Similarly, the other test like dynamic mechanical test, fatigue test, hardness, abrasion resistance, and these are all written. What these tests mean are written here. You can just read. Fatigue test is for determining the lifetime or durability. Hardness is the resistance to surface indentation. Abrasion resistance is the weightless by a fine abrader or the finely divided abrasive particle. But for this lecture, we will mainly talk about first two tests, which are used very often, and the rest of the test will not be covered because of lack of time. This will not be covered in this lecture. We are talking about deformation of polymer material. This deformation can be bring about in the polymer material in several ways, like tensile. You can pull a polymer specimen, you can compress them, which gives us a compressive deformation. You can shear them, and you can shear in rotational way as well. You can bend them, bend a polymer by applying stress in the middle of the polymer where the two sides are supported. You can apply this stress or so that there is this deformation happen oscillatory. That stress can be applied, or the deformation can happen in a tensile way or a shear manner. So, that is where oscillatory deformation is done. So, basically you must know this basic deformation modes to understand the subsequent test and polymer mechanical properties. So, let us talk about tensile testing. What is done? You take a specimen something like this geometry, which is like a dumbbell shaped geometry, or we call dog bone geometry in a crude way, and then fix these two sides and pull them, apply force from both the sides. Sample is deformed, the deformation is done at a constant rate, and the amount of stress is required for keeping that constant rate of deformation is monitored. So, stress is plotted against time or stress. Now, remember, in this test and all subsequent polymer property testing, you must, because this test is very much dependent on the size, shape of the specimen and the environment what you when you are doing the test, like temperature and relative humidity of the environment. So, you must there are agencies which give like ASTM and ISO, International Standard Organization, or ASTM, American organization, where basically they give specific conditions, specific size of the and shape of the polymer specimen and the conditions. So, we must, when we testing, we must keep those condition intact to get the reproducible or repeatable polymer property measurements. So, this is done with a fixed shape, this tensile test is done with a fixed shape, size and environmental condition, and elongation at a chosen or specified rate dn by dt. So, what is the typical stress strain curve look like? We can analyze a stress strain curve. So, stress is plotted against strain, and this curves basically shows what are the possible effect or possible deformation in a sample. This does not happen from all the sample, but this is shown here to so that you know all the different terms and related to this tensile testing. So, as you know, the first part is linear up to this point. So, this part is elastic, and from this slope you can get the elastic modulus of the material. This is the proportionality limit, and this is the point where yield happen. Yield means necking happens in the sample. So, beyond this stress or beyond this strain, the polymers start deforming permanently. So, up to this is a linear elastic limit, and up to from here to here it is non-linear elastic limit. So, you can, if you deform up to this point and then remove the stress, it will come back to the original state, but beyond this yielding point it will not come back to the original state. So, permanent deformation happens. So, this is a plastic. So, from this point to further onwards is a plastic deformation happening. Below this elastic deformation is happening. This is called yield point. So, the corresponding stress is yield stress and corresponding strain is yield strain, and on subsequent applying subsequent strain or subsequent straining, sometimes at the end the stress might go up further. That is because strain hardening taking place, the chains are already stretched. So, for further stretching of the chains become difficult, polymer chains become difficult. So, you require more stress to give a given strain, and this strain hardening, this is because of strain called strain hardening, and this slope sometimes can give us the strain hardening modulus, and this is the point where polymer breaks, polymer fails, they basically fell apart, and this is the corresponding stress is called ultimate stress, and the strain is ultimate strain, which is the strain or elongation at break. So, please remember all these terminologies. This is yield point, this is final break point. So, elongation at break, ultimate strain, and this slope, initial slope gives us the elastic modulus. Some terms related to tensile testing: stiffness, usually stiffness related to the product of modulus and the moment of inertia. So, basically if you have a specimen, you try to bend them, and if you feel resistance to bending, if you call this the material is stiff. So, that is depends upon the moment of inertia, which is given by the shape and geometry of the specimen, and if you compare between different material of same sample specimen, then higher the modulus, obviously higher will be the stiffness, higher will be the resistance to bend. So, this modulus is the material property, whereas the moment of inertia captures the contributant from structural design and the shape on stiffness. So, if you compare same structural design and shape materials, the higher the elastic modulus, higher will be the stiffness. Rigidity is the ability to carry stress without changing dimension, basically similar to stiffness, and the magnitude of elastic modulus is a measure of rigidity. Elasticity is the ability to undergo reversible deformation, means where that after the stress is released it should come back to the original state. That is what mean by reversible deformation, and or carry a stress without suffering permanent deformation, and is indicated by elastic limit or the yield point. Beyond yield point, the sample actually undergo permanent deformation. Strength is the load is a sustained, it is the ability to sustain dead load. So, basically ultimate strain is the stress it can capture or it can hold before it breaks, and yield strength is basically the stress it can take up before it yields, and toughness is basically the energy spent, the entire energy spent for causing the material fail. It is basically the area under those stress strain curve in case of a tensile testing. I just showed one example in last page of one type of stress strain curve, which basically capture everything, all the possible deformation of terminologies, but in typically one particular polymer can have one type of this deformation behavior. For example, polymer gels have this type of soft and weak stress strain behavior. This is hard and brittle, so it breaks at low strain elongation value. Similarly, this is hard and strong, this is strong and tough, and this is hard and tough, and example of these are given in this table. So, hard means higher elastic modulus, where soft means low elastic modulus, and weak and brittle is basically given by the elongation at break. So, high elongation means toughness value is high. So, these are different types of stress strains possible for different polymers. The examples are given here. Some more examples with the names of the polymers. This is nylon, PVC, HDPE, LDPE. Now, just to compare the values of the polymers with metals. For example, highly elastic polymers like rubbers, they have low modulus, so typically about 7 MPa. Stiff polymers which have higher modulus about 4 GPa, and metals is much higher. If you compare a polymer and metal is much more higher modulus. So, where in the applications where you require very high loading applications, where basically the part has to hold a very high load, basically polymer does not fare well in those applications. So, metal is the choice of material in those applications. Tensile strains for bulk polymers are less than about 100 MPa, whereas metals and alloys they are quite high. And elongation is where polymers win over metals. The polymers can elongate in case of elongation. Typically, polymers elongate much more than metals. Now, the stress strain curve we talked about, and the modulus or the stiffness and rigidity and your elongation at break, all those parameter or properties can actually depend both on the temperature and the time, the strain rate, basically how fast you are applying the stress or how fast you are straining the polymeric material. For example, this is a stress strain curve for polymethyl methacrylate, and as you can see the stress strain behavior changes. At a lower temperature it becomes hard and brittle, whereas at a higher temperature it becomes soft and ductile, which means the the sample can be elongated, it is more tough in that sense. Similarly, if you change the strain rate means the dl by al value, the first you are changing this applying the strain. So, your the first deformation will change the stress strain behavior. If the strain rate is higher, it will become closer to become hard and brittle, and if you do the deformations at a slow pace, then it will become more soft and ductile or tough in nature. So, basically you must know that the mechanical properties of polymers, this for example, stress strain curve and other mechanical properties always as well very much dependent on the temperature of the experiment. So, and finally, where this material is applied. So, definitely if you measure a modulus or stiffness at say 40 degree centigrade and find your material is sustaining the load, you probably may not use that at a higher temperature like 80 degree, you might see a failure because of decrease in the modulus of the material. So, that you must know that all the mechanical properties depend on the temperature of the experiment or the application and how fast the deformation is taking place or how fast the load is applied. So, just again showing the same thing with increasing temperature, the sample becomes tough and ductile, with reducing temperature it becomes brittle and rigid, whereas applying high strain rate makes the sample brittle and rigid, whereas low strain rate makes the sample tough and ductile. The modulus, which means the stiffness or the rigidity, very much dependent on the temperature, as I said. So, this is an example how the modulus changes with temperature. As we know that the polymers have undergo glass transition and melting transition at an elevated temperature. For example, if you have pure amorphous material, it undergoes glass transition at Tg, whereas semi crystalline polymers undergo both glass transition and melting at Tg and Tm subsequently. So, the modulus also changes with temperature. Generally, modulus decreases with increasing temperature of the thermoplastics, and at Tg and Tm the modulus decreases suddenly at T exceeded Tg and Tm, and with increasing crystallinity in case of semi crystalline polymers, with increasing crystallinity modulus goes up, and also for the cross-linked polymer with increasing degree of cross-linking the modulus goes up. So, with different, so this is a plot of log elastic modulus with temperature, which shows that different regions of polymer elasticity, whereas below Tg it is glassy, which have higher elastic modulus, and it is more of a elastic behavior, is like elastic behavior. Then immediately after the Tg it become soft, but the because of high viscosity the polymer chains still cannot move past each other very easily, and that is rubbery leathery state. And on further heating it reaches the viscosity comes down, and the polymer chains can move past each other quite easily, and that state is rubbery. And this is we are talking about a amorphous material, and at the very high temperature it behaves like a polymer liquid. So, it is basically flow state. This is example of real polymers. Nylon 6 is semi-crystalline polymer, is basically drops after Tg, it drops very fast, and then after Tm, this is a Tm. So, after Tm it's become polymer, the elastic modulus become very low after Tm. So, there is a Tg here, drop in modulus, and Tm, drastic drop in modulus in case of a semi-crystalline polymer. This is a pure amorphous polymer. So, the drop in elastic modulus or modulus after Tg, and this is a rubber with cross linking. So, it drops after Tg, but because of the cross linking, the presence of cross linking, the elastic modulus or modulus does not drop significantly after a value. So, this is what I was discussing in just a minute, that with for a semi-crystalline polymer with increasing crystallinity, the modulus goes up, elastic modulus goes up, where in case of cross linking material with cross linking, the modulus again go up further with cross linking. So, this is the way you can basically change. If you have a semi-crystalline material, you can increase the crystallinity to increase the load bearing capacity of the material, and if you can also cross link to increase the load bearing capacity even at higher temperature, but then cross links brings other problem like processability with it. These are the other mechanical property testing. We just discussed all last few minutes about tensile. Basically, the stress is applied in a longitudinal direction. Here in case of flexural or bending testing, it is basically bending mode where the stress is applied. It can be 3-point bending test or 4-point bending test. It is like stress is or strain is applied in bending direction. So, higher the modulus, the bending will be lower. We can we just talk about impact testing. Impact basically is a dynamic loading at very short duration. You know, we know about impact, like if you have just a glass, then if you hammer it, it breaks, which means the glass has a very low impact property. Glass, like we talk about glass, then if you keep glass and you can put a load on it, it does not break. So, the modulus of glass is high, because the strain rate or the stress you are applied is not in a higher rate, very fast rate. But when you apply the hammer on that, you are applying the stress in a much faster rate. So, you are straining the material at a very faster rate, and the material performs poorly, the glass perform poorly. So, the impact behavior of glass is basically poor. So, the glass impact behavior and modulus does not always match with each other. The testing itself is different. Modulus, we talk about the slow deformation, we do deformation or we apply strain in a much slower rate compared to a impact testing. So, impact testing is a dynamic load of short duration and very high strain at very high strain rate, and the performance of thermoplastic or plastic material depends upon the stress rate. Obviously, the higher it depends upon how you are applying the stress, loading rate, what is the amount of force, temperature, and sample geometry and nature of the sample, of course. There are different types of impact test available, which you have to, if you are applying a polymer, designing any you have made a polymer and you want to test, you have molded it and you want to test impact properties, then you need to know the target application. Depending on the target application, you choose the type of impact test should be done on that sample. So, different types of test possible, namely Charpy, notched izod, falling dirt, tensile and drop test, and they are basically different types of test. Charpy test is shown here schematically. You have a sample, the sample is clamped both the sides, and there is a notch in the other side, and you hammer it and find out the energy required to break the material. In case of notched izod test, you clamp this specimen up to the notch, this both side, and hammer on the top part. So, this material, this specimen breaks from the notch, and the amount of energy required to break this material will be the notched izod impact energy. Sometimes the test is done without the notch, where we say just izod testing, unnotched izod impact testing. In case of tensile testing, a tensile bar, a dog bone type specimen or a dumbbell side specimen is fixed one side, and another side with a pendulum is hit and the hammered from both the sides. So, actually the deformation or the strain happen in a tensile way, in a longitudinal way, uniaxial, it is a uniaxial test. So, the only difference between this and a tensile stress strain test, that here the strain is applied or the stress is applied much higher rate. So, the amount of energy required to break this bar is called impact strain. Another testing where a load is just applied, actually allowed to drop from a height on a circular disc, and it can break this material or it can make a hole, just hole, depending upon the energy, and the amount of energy required to break this material is again is impact energy for this plate. And drop test is basically take the specimen and drop from a certain height, which is very complex phenomena. Now, we know different tests, impact test, tensile test. Now, we need to find out what is the relations between the polymer structure and the properties. Now, as I said that temperature is a very important thing. So, we can compare for a same polymer, same chemical nature at the same temperature, elastic modulus will increase with crystallinity, as we have seen earlier, that for a particular semi-crystalline polymer, if we may want to increase the elastic modulus at a particular temperature, you increase the crystallinity. Or we can, if it is not a homopolymer, it is a blend of different phase. There is a basically there could be two, one a soft or rubbery phase and a hard or elastic phase. Basically, with increase the soft disturbed phase, the modulus increases. If there is a orientation, the chains, if the chains are already oriented little bit, obviously if you want to deform further, you have to you have to stretch the polymer chains further, which means what I am telling that this is the original state. Now, if I already have stretched and aligned, oriented little bit, then obviously aligning from or stretching, deforming from this state will be much easier compared to aligning from or deforming longitudinally from this state. So, orientation increases modulus, and for a semi-crystalline polymer, if we increases some glassy additives like glass fibers in amorphous region, then basically the elastic modulus goes up. Flexural modulus increases with elastic modulus generally flexural modulus and elastic modulus go hand in hand. So, with increase in elastic modulus of a plastic material, flexural modulus or bending modulus also go up. yield strength, that is the stress where yielding starts or permanent deformation starts, and again with yield strength decrease, if we add some plasticizer or a solvent molecule, obviously the yielding yield stress comes down. It increases just like modulus, it increases with crystallinity of a semi-crystalline monomer, and if you add these glassy additives like glass fiber, then yield strength increases. Elongation at break, decreases with increasing molecular weight, and elongation at break decreases with increases short change branching density of the polymer, and basically we relate brittleness of a polymer with elongation at break. Basically, when something elongate more, we say this less brittle, and if it does not elongate, we call that it is a brittle material. In general, if we talk about different polymers, if you want to compare the mechanical properties of different polymer, in general what happen if you have stiff polymer backbone, obviously stretching it further or deforming it further is always difficult. So, yield strength and the elastic modulus becomes higher. If it is a flexible backbone, obviously deformation is much easier. So, modulus come down. Similarly, if it is stiff, then you cannot deform it, you cannot strain it much longer, which means the elongation at break for a stiff polymer is low, whereas a flexible polymer will have very much higher elongation at break. In terms of impact properties, again if stiff polymeric backbone, if you apply impact, then with a short time the polymer cannot rearrange and absorb that energy. So, it breaks, it becomes brittle, whereas if you have flexible polymer chain, obviously it can absorb that energy and change its conformation. So, in general, if we want to summarize, flexible backbone, lower modulus and strength, change stiffness of the backbone or bulky side group, increases the modulus and strength, and change stiffness, lower the impact strength and elongation break. Now, with this I stop for this lecture. I will just continue the mechanical property in the next lecture, little more discussion, and we will talk about some other, we will start discussion about some other properties in next lecture as well.